In the previous lesson, we learned about solution and how we make solution with solute and solvent. In this lesson, we are going to look at a specific measurement and skill set to determine that concentration in the solution. Well, using a spectrometer and the Beer law, well, first of all, a spectrometer is used to measure the amount of light absorbed by a solution. Now, this light is absorbed at a specific wavelength, and different wavelengths are used for different solutions with different colors, because different colors absorb different wavelengths of light. Now, before we talk about that, okay, let's talk about what is happening in a spectrometer. Well, first of all, we put a solution in a cuvette, and a cuvette is basically a small vial with a known width. So basically I have a vial, and basically we know what's the distance from here to there. So that specific length or width is known to us because we're going to use that in the Beer law. Now the amount of light absorbed by a solution is called an absorbance. So we can measure absorbance. This is something that the spectrometer will show us. So this is something that we will measure, okay? We will measure absorbance. And lastly, different solution would have different molar absorptivity constant. And notice constant, that means it stayed the same. So let's talk about the Beer law, okay? First of all, the Beer law is basically capital A, which is your absorbance right here, equal to A, B, C. Now, what is A? A is your molar absorptivity constant, and this stays the same for the same substance, okay? So if you are measuring the same substance, the molar absorptivity would not change at all. So you keep that in mind. It doesn't change. And then we have our B. B is right here. This is the distance that light is traveling through the solution. Remember I drew this right here. This is your B right there. That's why it is important to have a known width of the cuvette or the small vial where we put our solution in. So this distance is given to us. And usually it's the same because we're using the same spectrometer. Now, what about the last one? The last one is what? The last one is concentration. This is our target right here. The concentration of the substance in the solution, or the concentration of the solute in the solution. This is what we're gonna look at most, okay? So in order to determine concentration, which is C, we have to look for A divided by AB, this right here, okay? So notice how big A represent absorbance, the little a represent molar absorptivity constant. Before we look at some sample problems, let's look at this ideas right here, where different colors of different solution will absorb different wavelengths of light. To be more specific, the color of the solution is complementary to the wavelength of the color of light that's being absorbed. So what is complementary color? Now, basically it is the opposite based on a color wheel. So in this case, for example, if the solution looked green, so we find where green is on the color wheels, and it's complementary to green, which in this case is the opposite of it, and that would be red. So what is the wavelength for red color? So that is between 630 to 750. So any light at that specific wavelength will be absorbed by the solution with the color green. So any wavelength between 630 to 740 will be absorbed by the solution. For example, in this case, it would be 680 nanometer wavelength, where the solution looks violet. Where is violet? In this case, right here. And what is a complementary color to violet, which is the opposite, in this case, yellow. So the wavelength that's being absorbed is between 590 to 560 or 560 to 590 in this case. An example would be 580. And one last thing we need to remember is that greater concentration will absorb more of the light. What is greater concentration? We are talking about more particles in the solution, okay? Because those particles or those ions will absorbing the light in the solution.